The universe is vast, an almost incomprehensible expanse that stretches beyond our wildest imaginations. Countless stars dot the cosmos, each a sun with its own family of planets orbiting in a delicate dance of gravity and time. Could we be alone in this immense expanse, or does life echo across the universe on other worlds waiting to be discovered? To answer this profound question, we must first understand how life arose here on Earth, our own blue planet. This is the story of abiogenesis, the incredible journey from non-life to life, a process that began billions of years ago. The origin of life is one of science's greatest mysteries, a puzzle that has intrigued and challenged the brightest minds. How did the first living things emerge from the primordial soup of early Earth, a mixture of simple chemicals and energy? It's a question that has captivated scientists and philosophers for centuries, sparking countless theories and debates. While we don't have all the answers, scientific inquiry has illuminated a path, revealing clues to this remarkable transition from chemistry to biology. Imagine a time when Earth was young, a fiery ball of molten rock still cooling from its formation, a hostile environment by today's standards. Volcanoes erupted with ferocity, spewing lava and gases into the atmosphere, creating a volatile and dynamic landscape. Lightning crackled across the sky, igniting the early atmosphere while the turbulent oceans churned with raw, untamed energy. It's hard to picture life arising from this chaotic scene, yet somehow, against all odds, it did. The story of abiogenesis is a testament to the power of chemistry and the incredible resilience of life, which found a way to emerge and thrive. From simple molecules through countless chemical reactions arose complex structures, eventually leading to the diversity of life we see today. Join me as we delve into this fascinating journey, exploring the key steps and scientific breakthroughs that transformed a lifeless planet into a world teeming with life, a journey that continues to inspire and amaze us. Picture Earth as a newborn planet still reeling from its violent birth. The surface was a chaotic landscape, a true cradle of chaos where the forces of nature were in constant turmoil. The surface was a maelstrom of volcanic activity, with eruptions that could be seen from space, painting the sky with fiery hues. Molten rock flowed across the landscape like rivers of fire, while volcanoes belched out noxious gases, forming a primitive atmosphere that was both toxic and dynamic. This early atmosphere was very different from the air we breathe today. It was a thick, suffocating mix of gases that would be deadly to most life forms we know now. It lacked oxygen and was rich in methane, ammonia, and water vapor. These gases created a greenhouse effect, trapping heat and keeping the planet warm despite the young sun's faintness. As Earth cooled, water vapor in the atmosphere condensed, forming vast oceans. These oceans were the first reservoirs of liquid water, essential for the chemistry of life. These early oceans were far from tranquil. They were turbulent, with violent waves crashing against the nascent landmasses, constantly reshaping the planet's surface. They were bombarded by asteroids and comets, delivering more water and organic molecules to the planet's surface. These celestial bodies acted as cosmic delivery systems, bringing essential ingredients for life. These impacts also generated intense heat, further shaping the early Earth. The energy from these collisions caused chemical reactions that would be crucial for the development of life. It was in this chaotic and volatile environment that the stage was set for life's emergence. The constant upheaval created a dynamic environment where new compounds could form. The building blocks of life, simple organic molecules, were present in the early Earth's atmosphere and oceans. These molecules, such as amino acids and nucleotides, are the precursors to more complex structures. These molecules, formed through both terrestrial and extraterrestrial processes, would serve as the raw materials for life's genesis. The interplay between Earth's environment and the materials from space created a rich chemical soup. While the conditions on early Earth may seem harsh and unforgiving, they were, in a sense, the perfect crucible for life's emergence. The extreme conditions provided the energy and materials needed for complex chemistry. The constant flux, the abundance of energy, and the presence of key chemical ingredients provided the necessary conditions for the remarkable journey from non-life to begin. This was a time of great potential where the seeds of life were sown in the fertile chaos of early Earth. The early Earth's atmosphere and oceans were like a giant chemistry lab with all the necessary ingredients for life to arise. However, these were just simple molecules. The key question is, how did these simple molecules assemble into the complex organic compounds essential for life? The answer lies in the unique conditions of early Earth. The energy from lightning, volcanic eruptions, and ultraviolet radiation from the sun provided the spark needed for chemical reactions to occur. These reactions caused simple molecules like methane, ammonia, and water to combine, forming more complex organic molecules like amino acids, sugars, and nucleotides. One of the most compelling pieces of evidence supporting this theory is the famous Miller-Yuri experiment. In 1952, Stanley Miller and Harold Yuri simulated the conditions of early Earth in a laboratory setting. They filled a sealed flask with methane, ammonia, water vapor, and hydrogen gas and then subjected it to electrical sparks to mimic lightning. The results were astonishing. Within days, the flask was teeming with organic molecules, including amino acids, the building blocks of proteins. This groundbreaking experiment demonstrated that the complex organic molecules essential for life could indeed arise from simpler inorganic precursors under the right conditions. With complex organic molecules like amino acids and nucleotides now present, the stage was set for the next monumental leap in the journey towards life. The next crucial step was the emergence of self-replicating molecules, a fundamental requirement for life as we know it. Here, a new protagonist takes center stage: RNA. This molecule, often overshadowed by its more famous cousin DNA, played a starring role in the early chapters of life's story. While DNA is now known as the hereditary material responsible for storing and transmitting genetic information in modern organisms, RNA, its close chemical cousin, likely played a pivotal role in the early stages of life. Unlike DNA, RNA is versatile and multifunctional. RNA possesses a unique ability. It can store genetic information like DNA and catalyze chemical reactions like an enzyme. This dual functionality makes RNA a prime candidate for the first self-replicating molecule. Imagine a world where these molecules could not only carry genetic blueprints, but also drive the chemical reactions necessary for life. The RNA world hypothesis posits that early life relied on RNA for both genetic information storage and catalytic activity. This hypothesis suggests that RNA was the original molecule of life, predating both DNA and proteins. In this primordial soup, RNA molecules could have self-replicated and even evolved, albeit in a much simpler manner than what we see today. These early RNA molecules were likely short and simple, but they held the potential for incredible complexity. Imagine a primordial soup, rich in nucleotides, the building blocks of RNA. These nucleotides, floating freely in the ancient oceans, were the raw materials for the first RNA molecules, the building blocks of RNA. Under the right conditions, these nucleotides could have spontaneously assembled into short RNA chains. This process, driven by the natural forces of chemistry and physics, was the first step towards life. Under the right conditions, these nucleotides could have spontaneously assembled into short RNA chains. Some of these chains, by chance, might have possessed catalytic properties, enabling them to facilitate the formation of more RNA. Some of these chains, by chance, might have possessed catalytic properties, enabling them to facilitate the formation of more RNA. This catalytic ability was crucial, as it allowed RNA to not only replicate itself, but also to drive other important chemical reactions, enabling them to facilitate the formation of more RNA. This self-replication, even if imperfect at first, marked a crucial turning point. It set the stage for natural selection to take hold, favoring RNA molecules that could replicate more efficiently and accurately. This self-replication, even if imperfect at first, marked a crucial turning point. It set the stage for natural selection to take hold, favoring RNA molecules that could replicate more efficiently and accurately. Over time, this process could have led to the emergence of more complex and stable RNA molecules. It set the stage for natural selection to take hold, favoring RNA molecules that could replicate more efficiently and accurately. This natural selection process, driven by the competition for resources and the need for stability, was the engine of early evolution, favoring RNA molecules that could replicate more efficiently and accurately. Over time, this process could have led to the emergence of more complex and stable RNA molecules capable of performing a wider range of functions. Over time, this process could have led to the emergence of more complex and stable RNA molecules, eventually paving the way for the evolution of DNA and proteins. These more advanced molecules took over the roles initially played by RNA, leading to the rich diversity of life we see today, eventually paving the way for the evolution of DNA and proteins. The transition from an RNA world to one dominated by DNA and proteins was a monumental step in the history of life, setting the stage for the development of complex organisms and the incredible biodiversity of our planet.